Hi guys, welcome back to my channel. I'm Mansur and today we are going to be discussing another pattern called the monotonic stack. Now this is another important pattern that is pretty popular for some algorithmic problems, the monotonic stack. The idea is simple. We have a data structure called a stack. So we have a monotonic stack. We have a data structure called a stack. You know what a stack is? A stack is a last in first out data structure. So we have a monotonic, we have a stack, and then what makes it monotonic is that the elements within this stack are in a particular order. We're going to make sure that we maintain the elements in this stack in a particular order. So the elements, each of these has to be in a particular order. So either the elements are increasing in a particular order or they are decreasing in a particular order. This is the concept of the monotonic stack. So let's take a really straightforward example that sort of illustrates the kind of questions where the monotonic stack actually comes into play. So a pretty popular question is, or the most easy case of a question is whereby you are given a question, an array of elements. Now this array of elements would be, say that you're given an array of elements of let's say 2, say 3, let's say 6, then 1, then 2, then let's say 9, then 3, then 12. Now you're given this array and then you are now told to return another array that contains the next greater elements within this array. So to put this into context, that will mean that in this case we have this entire so in this case we have this element. So the next greater element is 3. For 3, the next greater element is 6. For 6, the next greater element is not 1, not 2, 9. For 1, the next greater element is 2. For 2, the next greater element is 9. For 9, the next greater is not 9, it's not 3, it's not 12. It's not 3, it's 12. For 3, the next greater element is 12, and then for 12, so 12 basically has no greater element. So this is the idea of this problem. So it just says you're given an array and then you're supposed to figure out the next greater element after this array to its right. So now how do you solve this problem in a pretty efficient way? Alright, so ideally you probably say, if you were to implement this naively, you could have the idea of having 2 loops also. One loop that will go from I is equal to 0 all the way to the end of the array, and then another loop that will then loop through a second time and then go from the next position in I plus 1 all the way to the end of the array, and you just check. So you keep looping j until the element at that index of j becomes greater than the element at the index I. At that point you stop and then you fill up the position of this new array with that value. So now we have 2 for loops here. Technically you could imagine that you have an entirely increasing array such that you have 2, 3 here, you have, say here you have 7, you have 8, that's not even a good example. Say that you have an array of this, you have, and then you have say you have 13, 12, 11, 8, you have 6, you have 5, then you have 14. To determine the next greater element here for each of these, you technically, so using this approach, I will initially start here and then j will move all the way to the very end to eventually find that 14 is the next greater. Then you repeat the same thing again for I. for I is at index 2, index 1, I mean, that's pointing at 12, and then J will be at the next position, and then it continues to increase until you realize that 14 it is. So basically, you are going through the entire array for every iteration. This is going to be an S square. This is bad. You can do better than this. So this is where the monotonic stack shines. Now, the idea of solving this problem is, what if we maintain a stack data structure such that the elements within the stack, they are in a let's say a strictly decreasing order, right? So that means that the element at the very bottom of the stack, is, so let's say, so this is our E1, this will be our E2. So the element here, yes, this one has to be lesser than the elements at the next position. Right, okay, no, that is wrong. So in this position now, the element at E1 has to be greater than the element at E2. So E1 has to be greater than E2. We maintain this monotonic stack such that E1 is greater than E2. So this way, knowing that E1 is greater than E2, so at every point, what we will now do, what our algorithm will now do is that we are going to look through every index position. And as we look through every index position, we continue to add those elements that we are looping through into this stack, into the monotonic stack. And as we add these elements into the monotonic stack, we need to ensure that the elements within the stack are larger than the element that is coming into the stack. However, once we find an element that once we find out that the element we're about to add at the top, into the top of the stack is greater than the elements within the stack, we need to pop out the element and continue to pop out those elements one by one until we can no longer pop out. Until we can no longer pop out means that either the stack is empty or the elements that we're adding into the stack is now lesser than the elements already in the stack. Okay, so we'll run through an example so that it sort of makes sense and we can drive home the point. So imagine that we first have an array of these elements. We have this same element here. Then we have the stack. This will be our monotonic stack. Remember, the invariant is the elements within the stack have to be greater than the element that is coming into the stack. Yes? So now we start our iteration from I is equal to 0. So what we do is when I is equal to 0, what we do is we'll check inside the stack if the stack contains an element that is lesser than these two. This stack right now is empty. So we can just go ahead, just add it to the stack. Now we have the next, our I position now moves to the next index. Now I is 3. We do the same thing for 3. We check inside the stack. Does this stack contain an element that is lesser than this 3? So let's actually write that out so that that's clear. Does the stack contain a value less than incoming value? So now we see that the value that's coming to the stack is 3. This 3, let's direct it. So now this 3 is what is about to come into the stack. And then we ask this question: does this stack contain a value that is lesser than 3, the incoming value? Yes, it does. So because it contains a value that is lesser than 3, what we really do is that we need to remove out the value from this stack, pop it out, get it out of the way, and then immediately go to the new array that we are creating and then set the value in that position to the value that's coming in. To say that, okay, so this is the next greater element after 2. Are we seeing? Are we getting the idea? Then we now that the stack is now empty, we do the same thing. We can now insert the value 3 into the stack. Stack is now empty, so now we can insert the value 3. Now we have 3 in the stack. We then move to the next index position, which is 6. Repeat the same process. This value of 6 that's coming in, is it greater than the value already in the stack? Yes, it is. So we need to pop out this 3 and then insert into the index position for 3 the value 6. Then we push 6 onto the stack. Now that 6 is the next value on the stack, next thing for us to now do is we move the value I into the next position, index 1. Then we check, attempting to add 1 into the stack. Does this stack contain a value that is less than 1? Right now, it doesn't. So we add 1 onto the stack. Then we move on to the next index position. We say, does this stack contain a value that is less than the incoming value now, which is 2? Yes, it does. 1 is at the very top of the stack. So we pop out this 1. We go to the index position of this one and we insert the value 2 that's coming in. So a very important point here is, I don't know, you guys must have noticed, is that we do not actually need to store the exact value within the stack. What we need to store are the indices. We need to store the indices of this value, knowing that those indices are what we will use to insert the next greater element within the new array that we are creating. Just take a minute to replay this so that this makes sense. This is a very important part of the idea of the monotonic stack. We store the indices so that we can go back to that index position and insert the new value. Alright, so now at this point, we no longer have 1 within the stack, and then we can just remove this element from the stack and then ask the same question. Does this stack contain an element that is lesser than 2, the incoming number? It doesn't. 6 is the number that is greater than. And the good thing about the monotonic stack is, since we maintain the fact that the element at the bottom will always be greater than the element at the top, that means that even if this stack contains any other value, it cannot contain, or if there's any other value below 6, the value cannot be lesser than 6. It has to be a value that is greater than 6. Say 8, 9, That is the concept of monotonic stack, which means that we no longer need to compare the value that is incoming, the 2, with any value that is below. It is sufficient to just compare it with the value at the top. This is what makes the monotonic stack a really powerful data structure. Okay, so now that we've evaluated for 2, we move on to the next index, which is for the value 9. Now for the value 9, we ask the same question. Does this stack contain a value that is greater than, does this stack contain a value that is lesser than 9? Yes, it does. So we need to pop out this value at this index position and then go to that index position and insert the number 9. We pop it out, we insert 9 to the index. So now that we popped out this value, we need to continue to repeat this process all over again. We compare 9 to the value at the top of the stack and realize that 9 is greater than this value. So we need to pop out this value, go to the index position and insert the value 9. You guys with me? Okay, so now that we've processed for all of this, the stack is now empty. We can now add back 9 into this data structure. So remember, so now to do things more correctly, actually we are not adding 9 to this stack. We are adding what? We are adding the index position of 9, which is what? The value 5. So 5 is actually what we are going to add here. Remember, the indices is what gets stored. So now we move I to the next index position. 3. We say, does this star contain a value that is less than 3? Right now, it's as simple as checking the top of the stack and comparing the value at the top of the stack, the value at that index. Yeah, the value at the index 5 now is 9. And we compare this value with the value that's coming in 3, and realize that the value is greater than 3. So we do not need to remove any element from the stack. We just add the index position of 3 to the stack, which is 6. Then we move I forward up to the index position, the last index position. At this point, we realize that we have the number 12, and we ask ourselves the question again: does this stack contain a value that is lesser than 12? Yes, it does. This stack contains the value 3. So at the very top of the stack, we have the index position 6. The value at that index position 6 is 3, and 12 is greater than 3. So what do? We need to go to the index position for 6, that index position 6, and insert the value 12. Then we pop out that value from the stack. Repeat the same process again. Does this stack contain a value that is lesser than 12? Yes, it does. The value at index position 5 is 9. That 9 is lesser than 12. So we pop out that value from the stack, go to that index position of 5, and insert the value 12. Now we have 12 inserted at this index position, and then we can now easily pop out. We can now easily just insert the value 12 onto the stack. Now we insert the value 12 onto the stack. We increment our I pointer, and then realize that we are at the end of the array has ended. So now at this point, we can now pop out this index. So this is the index 7. We can now pop out this index value, and then based off of what the question has directed us, insert some default value in this position. So if we compare this value that we have, we see that this exactly matches what we did before with the brute force approach. The only difference is this is now far more efficient. You can see this is 3, 6, 9. This is 2. This is 9. This is 12. This is 12. And in this position is some default value. This is the idea of the monotonic stack, a very important data structure that allows us to answer some other important queries, like the next greater element, the next lesser element, even a range of greater and lesser elements. A very important data structure. So I will employ you guys to practice more with this pattern so that you can own your skills. Thank you very much for joining me once again, and I'll see you guys in the next video, where we'll be discussing the top key elements pattern. Don't forget to like, share, and subscribe. See you guys once again. Bye bye.